Welcome to the short presentation of my doctoral paper, Decentralized Self-Adaptation in Large-Scale System of Systems. In this presentation, I'd like to give you an overview of my current plans for my thesis. As this is the doctoral paper, I also talk about my plans and expected contributions. The presentation is lined out like the following. I'd like to start with a short introduction on myself. Then for the actual talk, I will start explaining the motivation behind my thesis and explain some important foundation in order to understand the research gaps. Afterwards, I will present the research points, which are still very broad in this moment, and talk about potential concepts to be used. In the end, I will say some words about the methodology and evaluation and make a short conclusion. I would like to begin with a very brief introduction of myself. My name is Matusek. I'm a PhD student at TU Dresden and currently in the first year of my PhD. I'm a part of the research training group called ROSI, which is short for Role-Based Software Infrastructure. The overall goal of ROSI is to model and implement software systems that use role-based and context-aware programming. My doctoral paper is a representation of my early ideas I gathered during the first steps and initial literature research and presents my plans and next steps. This is the first conference I ever attend, and I am glad to have the chance to present you my ideas at this doctoral symposium. Let's start with the motivation behind my work. Nowadays, the number of IoT devices and collaborating autonomous systems is rising. Those consist of heterogeneous participants, are geographically distributed, and need steady maintenance. To tackle this problem, self-adaptation could be used. Self-adaptive applications monitor themselves in their environment and analyze the state to adopt the internal structure and behavior to the changed context. Nevertheless, many proposed systems use a central instance to control the adaptation, which potentially increases the possibility of bottlenecks and communication overhead. Additionally, a central coordination instance introduces a single point of failure. Therefore, a decentralized solution for coordinating adaptation increases robustness and allows for improving the scalability of those systems. Current approaches still have remaining challenges. Next, I would like to introduce the problem scenario. Next to Z and N, which will also be considered throughout the thesis, this real-world scenario gives us an idea where the problem can occur. The scenario is based on trucks which are organized in convoys to achieve a common goal. This could be, for example, fuel saving by driving behind each other. The trucks can communicate with each other, but those connections could be disturbed and prevent the message exchange between them, or can lead to the isolation of single trucks because they lost connection to other members of the convoy. The subsystems of the SOS can get divided in even more subsystems and get partitioned. The emerging subsystems must be able to reorganize themselves and possibly connect to the originating convoy later again. Convoy 1 gets divided into new subsystems which operate independently now, as you can see in the top picture where it gets divided. Now I would like to say a few words about the most important foundations for the PhD project. You can find the references in my paper. Throughout the thesis, we will use the notion of roles. Role-oriented programming allows us to dynamically bind and unbind objects during runtime to perform runtime adaptation without any downtimes. Additionally, we can express context-dependent and collaborative behavior of objects. To keep it short, an object enriched with a role can act according to its played role and extend its original behavior by the properties of the role. Another very important theoretical background is the work of Weisbach and others about coordinated decentralized self-adaptation. Every node has its adaptation manager, which is responsible for invoking adaptations on the node runtime and is communicating with the adaptation manager on other nodes. The adaptation process is performed transactionally and atomically, which means that every participant must agree on the adaptation and perform it successfully, otherwise the transaction will be rolled back. It is important that every adaptation manager is allowed to invoke adaptations. With this scenario and foundations in our minds, let's switch to the research gaps and goals throughout the thesis. Recap the error cases I presented a few minutes ago, where new subsystems can emerge either through error on purpose for self-optimization. As we can see in the right-hand picture, Convoy 3 got separated from other convoys due to connection shortage and other errors. Convoy 1 and 2 could perform adaptations in the disconnected time, which are contradictory to the changes which could happen on Convoy 3. Next to the general goal of state synchronization, an interesting idea in my opinion could be investigating the concept of conflict-free replicated data types for self-adaptive systems, which we could use to replicate the states on the different devices and use to achieve a common goal consistent to the system. Conflict-free replicated data types are now used for systems like Google Documents, where people can edit documents together even when members are offline. The documents are replicated for each member. Subsystems and systems of systems can be the result of errors and connection faults, which partition the system. Those independent partitions take their own adaptation decisions and thus drift away from a consistent state. After reintegrating the subsystems, a synchronization might be necessary to unite all system parts together to a single system again. This problem is very closely related to the first problem I presented and should be investigated together. We can tackle this problem also with CRDTs, since we want to recover a consistent state after self-adaptation took place, after a node or connection failure. In this case, this does not necessarily mean that concurrent adaptation took place, but it remains an open question how a subsystem, means convoy, adapts to other changes in the system to achieve a common valid global state again. The goal would be a protocol extension from the Weisbach protocol I presented you in the beginning, in order to replay adaptation in a correct way. We will need to define constraints and rules how this can be done, since we do not want to simply override the configuration of a convoy right after reconnection to the whole system. Now I want to discuss the next problem. For a decentralized adaptation protocol, it is important to investigate the hierarchy and distribution of leaders. In the exemplary decentralized adaptation protocol from Weisbach, every participant can act as a coordinator in the system and thus invoke adaptations regardless of its convoy or positions. It is questionable if this is suitable for a system of systems, where a system is divided into multiple subsystems, because the communication overhead could increase and the chance of concurrent adaptation is higher. An analysis of the architecture pattern for decentralized adaptation from Danny Waynes and others would be interesting. With this in mind, it would be interesting to search for a suitable leader election mechanism depending on the elaborated hierarchy suitable for decentralized system of systems adaptation. The last research gap and problem I want to talk about is consensus and atomicity of decentralized adaptation transactions. The presented approach is using the concept of atomic adaptation transactions. Now imagine a large distributed system, like our scenario with convoys of trucks. Almost every node accepts the change but one. With the current approach, the change would be reverted. If we introduced a concept similar to base in databases, we would accept a certain level of inconsistency and let one of the failed node cope the error to adapt to the others after a certain amount of time. It would be interesting to investigate the concept of eventual consistency for self-adaptation transactions. Now I would like to say some words about the methodology and the evaluation I have planned. As you might have seen, the topics are still very broad and need a stronger focus. I plan to focus on two research questions, either on coordination of those transactions or on the consistency and error cases. We will simulate those trucks by using the Weebot simulation environment, and on top we will implement a decentralized adaptation mechanism as a baseline. This will be used for an investigation about leader election and hierarchies, as we will plan some experiments on research on this. It is also imaginable to make research in the direction of base transaction concepts for decentralized adaptation transactions. The evaluation will be made in the Weebots environment and also experiments on ZNN, as it is accepted in the community. Let us come to the end of my presentation with a brief conclusion. Decentralized self-adaptation systems of systems still has some remaining open challenges. My thesis will focus on making self-adaptation a large-scale system of systems more robust and feasible. As I still have many points and this is quite a broad research proposal, I need to focus more on either coordination or consistency. Our goal would be to develop a protocol for efficient, fault-tolerant, decentralized self-adaptation system of systems. As outcomes, after my time as a PhD, I expect the mentioned protocol and understandable results from experiments about leader distribution hierarchies in system of systems. Also, I want to measure the impact of base-like transactions for a large system of systems. My deadline is in September 2022, which means that I need to specify my topic in the next time to start research and contribute in these topics. Thank you very much for your attention and watching this video, and I'm looking forward to an interesting discussion with you.